Hello students, welcome back to the classroom point. In our previous class, we have discussed about the Planck's quantum theory and its calculations. Now, in today's class, we are going to discuss the photoelectric effect and how this photoelectric effect proved the particle nature of the electromagnetic radiation that was given by the Planck. So, both we shall see now. Photoelectric effect. So let's have the definition, then we shall see the experiment. Photoelectric effect means when a light of suitable frequency hit the clean metal surface, electrons are ejected from the metal surface is known as photoelectric effect. So this is the definition of the photoelectric effect, which says that when light of suitable frequency hit the clean metal surface, electrons are ejected from the metal surface. So let's have the small diagram which describes this photoelectric effect. Here there is a glass tube in which we take the metal plates. This is our target metal, which is acting as cathode. And here this metal plate is connected to the battery and acting as anode. So here the concept says that whenever light of suitable frequency hit the clean metal surface. So what's happening here is electrons are ejected from the metal surface instantaneously. So this phenomenon, that means striking of the light on the metal surface and ejection of the electrons simultaneously, this phenomenon is known as the photoelectric effect. And here, whatever the metals we are using for this purpose are known as photosensitive metals. And the electrons thus released are known as the photoelectrons. Whatever the electrons are released, these are known as photoelectrons. And these electrons travel from negative part to the positive part so that they supply the current. So electrons move this direction and current moves in the opposite direction. So the current that moves in the circuit is known as the photoelectric current. This is known as photoelectric current. So, but if we see the phenomenon like this, we should come to know why after striking the light on a metal surface, electrons are ejected. Then we must recollect two things here. One is the Planck's quantum theory. Second one is Rutherford's atomic model. So in Rutherford's atomic model, we have studied that the center part of the atom is nothing but nucleus, which has the positive charge, and electrons revolve around the nucleus in the circular paths. So this completely fills the atom now. So electrons are carrying the negative charge here. The question here is, we know that electrons are carrying the negative charge and nucleus is carrying the positive charge. These two are opposite charged ones. So there must be some attraction between these opposite charges. Now if you want to bring this electron out of the atom, you must overcome this attraction force. So to overcome this attraction force, we must and should give some energy to the electron to come out. So the energy required to overcome the nucleus attraction power here is known as threshold energy. Threshold energy, it is represented by E naught. It is, if in terms of frequency, if you want to call, this one is known as the threshold frequency, nu naught. In terms of wavelength, if we call this one as threshold wavelength, lambda naught. And it is also known as, this threshold energy is also known as the work function, or also represented by the another symbol phi. Since electron being removed from the atom, it gets ionized. That's why this is also known as the ionization energy. So all these terms can be used in this case. Now the question is, so what amount of energy we have to send here? Look at this side. So when light of certain frequency hit the clean metal surface, we know that according to the Planck's quantum theory, see, photoelectric effect supports the particle nature of the light that was given by the Planck's. So that light is the form of energy which carries the photons. So these photons instantaneously transfers to the electron, means electron immediately absorbs the light energy in the form of the photons, so that the velocity of the electron that is revolving around the nucleus increases, energy also increases. So that energy, using that energy, electron try to overcome this nucleus attraction power. The question here is, how much amount of energy we have to supply here? And before that, we should call this one, whatever the light that hits the clean metal surface is known as the incident light, or else incident radiation. So that this energy is represented by the symbol EI, that is incident energy. In terms of frequency, if you want to call, this is called as the incident frequency, that is nu I. In terms of frequency, it is known as the incident frequency. In terms of wavelength, it is called as the incident wavelength. Now, whenever energy, this light is carrying some energy and that energy is given to the electron, whether all type of radiations will send this electron out of the atom or not, that means it is no. The reason is, whatever the energy you are giving to the electron, that energy not only increasing the energy of the electron, but also that energy must and should help to overcome this nucleus attraction power. Imagine the energy required by the electron to overcome the nucleus attraction power. In this case, I am taking as 5 joules. So that whatever the energy we are giving, that must be more than the 5 joules. For example, let us take the different cases here. So in case 1, if we are giving the 4 joules of energy, we cannot see any photoelectrons are ejected. But this 4 joules of energy helps the electron to increase its velocity around the nucleus. So that number of rounds also increases. It will go to the next higher energy level, but the electrons will not come out. That means electrons completely cannot overcome the nucleus attraction power. Then what about the second case? If you take the 4.5 joules of energy, here also no photoelectrons are observed. And third case, 4.99 joules of energy, again no photoelectrons are observed. When you give the energy that is equals to the at least incident energy, so 5 joules of energy is given. So that electron also requires only 5 joules of energy to overcome the nucleus attraction power, so that electron will get ejected out of the atom. So the ejected electrons are known as the photoelectrons. since these electrons are ejected using the light. That's why these are known as the photoelectrons. So photoelectric effect is observed. Then what is the velocity of the ejected electrons? Now in this case it is 0, because whatever the energy you had given, that entire energy was utilized by the electron only to overcome the nucleus attraction power, so that electron will not have any amount of energy to increase its speed. So that kinetic energy of the electron in this case can be taken as 0. Now let us imagine if you take this 6 joules of energy is given. That means intensity of the, that means energy of the incident light is 6 joules. So when 6 joules is used, then electron will take 5 joules of energy to overcome the nucleus attraction power. Remaining 1 joule of energy will be used by the electron to increase its speed. So this is for the kinetic energy. Now let us take another case. If 8 joules of energy is given, incident energy, then again 5 joules of energy was used by the electron to overcome the nucleus attraction power. Remaining 3 joules of energy helps in increasing the kinetic energy of the electron. Now let us take one more case, that is 10 joules of energy is given. Again 5 joules of energy to overcome the nucleus attraction power, and remaining 5 joules of energy helps in increasing the speed of the electron. So in these parameters, photoelectric effect is not observed until it reaches its threshold energy. Once threshold energy is reached, then photoelectric effect is observed. And here one more thing is, the threshold energy remains constant for a particular metal. So it is the characteristic of the metal. That means when you take the different metals, they will have the different threshold energy, because when element changes, nucleus power changes, so that the energy required by the electron to overcome the nucleus attraction power also changes. That is the reason why, so when elements changes, the threshold energy also changes. That's why here we have written that it is a characteristic of the metal. Now here what we can see, another thing is, whenever you are increasing the energy of the incident light, it is increasing the kinetic energy of the photoelectrons. So we know that energy is directly proportional to the frequency. So when the frequency of the incident light increases, it increases the kinetic energy of the photoelectrons. But you cannot remove the more number of photoelectrons. Why? Because one photon can remove only 1 mole of electrons. Means 1 mole of photons can remove only 1 mole of electrons. If you want to increase the number of photoelectrons, then you have to strike this metal surface with more number of photons. So when the number of photons increases, automatically brightness of the light also increases. When brightness of the light increases, that is what called the intensity. So intensity of the incident radiation also increases. So what happens when intensity of incident light increases, number of photoelectrons released also increases. So that here we can write down that the kinetic energy of ejected electron depends on the frequency of incident light, but not on the intensity of the incident light. At the same time, number of photoelectrons depends on the brightness, that means intensity. When brightness increases, more rays are coming, so that more electrons will get ejected. So here we can write down that the number of ejected electrons depends on the intensity of incident light but not on the frequency. Why? Because whatever the frequency you are increasing, frequency increase means energy also increase. So the increased energy helps in increasing the kinetic energy but not releasing the more number of photoelectrons. So now from this combination, what relation we can develop? That means, see here, energy of incident light now can be used. See here, 6 is equals to 5 plus 1. 6 means energy of incident light. 5 joules means threshold energy. And 1 joule means kinetic energy. So that we can write down that 6 equals to 5 plus 1. 6 means energy of incident light. 5 means threshold energy, that is E naught plus kinetic energy. This is the equation. Now this equation can be changed, means by substituting these values, kinetic energy value and E values. So we can write down that this EI can be written as H nu I, where nu I is the frequency of the incident light, that is equals to H nu naught plus kinetic energy. Then under what condition this photoelectric effect can be observed? As I said, the energy must and should be, the energy or frequency must and should be greater than this threshold energy or threshold frequency, but not less than. So that photoelectric effect can be observed when nu I is less than nu naught. No photoelectrons are observed. But when nu I is greater than or equals to nu naught, photoelectric effect is observed. In this case, in the place of this nu I or nu naught, we can use EI is less than E naught. Here we can write down that EI is greater than or equals to E naught. So under these conditions, we can observe the photoelectric effect. Now let's come to the derivation here. So H nu I is equals to H nu naught plus Ke. If you would like to calculate the kinetic energy, that equals to H nu I minus H nu naught. So kinetic energy can be calculated using this formula, and kinetic energy also can be calculated using another formula that we know, that half MeV square, mass of the electron, velocity square. Now if you want to draw a graph here, we can see that this kinetic energy, if you take on the y-axis, see this is mx plus c. So the graph comes like this. So in this, on y-axis we take kinetic energy. On x-axis we are going to take the frequency of the incident radiation. Now, as I said, kinetic energy depends only on the frequency of the incident radiation, but not directly. So that here we can get the, see here, positive slope is there, but intercept is negative, so that we get the graph like this. So in which we can write down that this value, whatever the intercept value is there, this intercept value is equals to C, that is minus H nu naught, and slope is equals to Planck's constant. Now let us try to substitute the lambda values also. Instead of the nu and nu naught values, let us substitute the lambda values also, so that if you get kinetic energy is equals to Hc by lambda I minus Hc by lambda naught. Hc is constant, so that we can take the Hc kinetic energy equals to Hc into 1 upon lambda I minus 1 upon lambda naught. Further simplification, you will get the Hc into lambda naught minus lambda I divided by lambda I lambda naught. So when wavelengths are given, we can take the graph like this. Now one more concept here. The number of See here, the kinetic energy of the ejected electron depends only on the frequency, so that the kinetic energy versus frequency graph, but not on the intensity of the light. It is independent on the intensity of the light, so that if you draw a graph between the kinetic energy versus intensity, so kinetic energy is independent on the intensity of incident radiation. So let us continue the concept. Here we are going to discuss about the why we are using the battery in this diagram, that we did not discuss in the starting part, because again we shifted to this diagram where how these electrons are released and what are the relations among the different parameters of the formulas. Now here is we are going to discuss about the stopping potential and what is the reason of the using the battery. See, as I discussed here, 5 joules of energy when hit the clean metal surface, electrons are ejected. So these electrons are not having any kinetic energy to travel up to the anode, so that no photo current can be observed. So to observe the photo current, you need to apply some potential difference, so that electrons can be absorbed or attracted by the positive electrode, so that circuit completes. So that here we are using the battery. Now, stopping potential concept. What is the stopping potential? Since stopping potential also related to the same diagram, that's why I'm discussing here only. Stopping potential in this sense, see, electron is coming. Imagine 1 joule of energy is enough for this electron to travel up to the anode. But I don't want this electron to travel up to the anode, I want to stop the electrons. So for that purpose, I need to apply some potential difference, that is V0, and change these positive and negative signs. So when you change, automatically potential difference will be applied. So when you apply some potential difference, that is the minimum potential that is to be applied to stop the electrons to reach the anode, is known as the stopping potential. Already electrons are traveling with some kinetic energy, that is kinetic energy maximum. We want to stop this electron to reach up to the anode by applying some potential difference, that is EV0. V0 is the potential voltage what you are applying against the charge. So kinetic energy, maximum kinetic energy equals to EV0. Means when this much potential difference is applied, this will stop the speed of the electron, so that it becomes completely zero. So stopping potential main intention is to make the kinetic energy of the electron is equals to 0. So in this case, kinetic energy already formula we have derived, that is h nu I minus h nu naught. So that I can write down that formula here. H nu I minus h nu naught is equals to E V naught. Now here, what is the V naught and on which V naught depends? This potential difference depends on the kinetic energy. This kinetic energy means more kinetic energy the electron is having, the more potential or voltage you have to apply to stop the electron. When it is coming with less speed, less energy is enough to stop the electron. When it is coming with the more speed, then you have to apply the more voltage. So the stopping potential depends on the kinetic energy, and kinetic energy depends on the frequency. So that again here V0 value also depends on the frequency of the incident radiation. So we shall draw a graph. I'll erase this one. Anyhow, this work is not there now for us. I'll erase this one and we shall have a graph about this one. H nu I minus H nu naught is equals to E V naught is there. Now V naught is equals to H nu I minus H nu naught divided by E. Now it looks like that is Y equals to M X plus C. Here I am going to draw a graph between the V0 versus nu I, so that the graph comes in this fashion. So here the graph parameters what I am going to take on the y-axis is voltage that is to be applied V0, and on the x-axis I am going to take the nu I, that is frequency of the incident radiation. So that nu I value I have taken here, it has the positive slope with a negative intercept, so the graph comes like this. And here the intercept value is minus h nu naught by E. And what about the slope value? Slope value is equals to h upon E. If you compare these two graphs, V naught versus nu I and kinetic energy versus nu I, the graph looks same. Only difference is electron voltage, whatever the electron is there, that charge differs. So here their slope is h Planck's constant, here slope is h upon E. Their intercept is minus h nu naught, here intercept is minus h nu naught by E. Now let us see what other information we can get all this from all this. See here, as I said, threshold energy or work function W, because in most of the cases they used to ask the work functions only. So this work function is nothing but h nu naught. So that in the place of E naught, I can use any of these parameters. E naught can be used, or W plus Ke I can use, phi plus Ke I can use, or else ionization energy plus kinetic energy also can be used. So now work function is equals to threshold energy. Now work function is equals to threshold energy means h nu naught. If they ask work function to calculate by giving some values, so that we can use this one. So W equals to hc by lambda naught. All these formulas can be used to calculate work function or threshold frequency. And classical physics says that according to the classical physics, whenever intensity increases, so brightness increases. When brightness increases, energy also increases. When energy increases, it says that number of photoelectrons released increases along with the kinetic energy also that is associated with the photoelectrons. So this is what classical physics has given the information. So how this phenomenon proved wrong later? So let us see that also here. Potassium metal threshold frequency is 5.0 into 10 power 14 hertz. Threshold frequency of the potassium metal. So as according to the classical physics, when brightness increases, intensity increases and energy also increases, so that number of photoelectrons and kinetic energy also increase, because here intensity, brightness and energy are correlated. They are directly proportional for one another. Now they have used the potassium metal, electron is there, this threshold frequency is 5.0 into 10 power 14 hertz. So they tried to use the red light. So when red light is used, I will use the red color so that so they used the red light. Red light has the frequency range, that is 4.3 into 10 power 14 hertz to 4.6 into 10 power 14 hertz. That means when red light is a dull in color, its frequency is 4.3 into 10 power 14 hertz. When brightness increases, then its color, brightness or redness also increases, so that its frequency is 4.6 into 10 power 14 hertz. So red light, by using the any color of the red light, even increasing the highest brightness of the red light, no photoelectrons are observed in this case. At the same time, they used the yellow light. So yellow light frequency is 5.1 into 10 power 14 hertz. Even dull yellow color, when they used, the photoelectrons were observed. So from this it is very clear that so the intensity, brightness, though they are related, but the energy is not directly related to the wave that is carrying the particles. So this intensity increase the energy, but not the energy of the particular wave, but the energy of the entire area it increases. So that is what we are going to discuss, the intensity. So this is about the photoelectric effect. As I said earlier, this photoelectric effect is related to the bond energy. How we can use this similar concept of the photoelectric effect in the photo dissociation. So that we shall see now. Photo dissociation stands for, photo stands for the light. This stands for light. Dissociation stands for the breaking. Breaking of what? Here breaking of the bonds using the light energy is known as the photo dissociation. So here we shall discuss one more important thing, that is the definition of the bond energy. The minimum amount of energy required to break 1 mole of a particular type of bonds known as bond dissociation energy. So let us take a molecule A is there is a 1 mole of the bonds. So to break these bonds we have to send some amount of energy. So the amount of energy whatever is going here, if that is sufficient, that will separate both of these atoms of the molecule as the atoms, so that both will separate as A plus A. So this must have the some amount of energy. So after giving some amount of energy, that is what incident energy, there also we call the incident energy. So this incident energy helps in the breaking separation of the atoms by breaking the bond. So let the amount of energy to require the break of 1 mole of the bonds is known as the bond dissociation energy. So 1 mole means for Na number of bonds, that means 1 mole. To break the Na number of the bonds, imagine x kilojoules of energy is required. To break 1 bond, how much energy is required? So here we can write down that energy required to break 1 bond is equals to cross multiplication x upon Na kilojoules. You should remember one thing, that 1 photon can break 1 bond. 1 mole of photons can break the 1 mole of the bonds. So this 1 photon energy is nothing but E equals to h nu. So that here also energy required to break the 1 bond is nothing but the energy of the 1 photon. So x by Na is equals to, we can write down that n h nu. N means 1, so that h nu it is. So x by Na is equals to, we can write down that h c by lambda. So the energy required to break the 1 bond can be calculated if energy of the incident radiation or photons are given like this. Now the question is, how can we relate this information with the photoelectric effect? Though both are not same, but it looks similar. So after giving, see here, to break this bond, imagine I need 30 kilojoules of energy, but I am sending 40 kilojoules of energy. The incident radiation what I am sending is 40 kilojoules of energy was used to strike this bond. Out of this 40 kilojoules of energy, 30 kilojoules of energy was utilized by the molecule to separate these atoms, and remaining 10 kilojoules of energy helps in increasing the kinetic energy of both of these atoms. So that here I can write down that energy of the incident radiation is equals to bond energy plus kinetic energy. And if they ask you to calculate the kinetic energy of every atom, so kinetic energy is equals to incident energy minus bond energy divided by number of atoms in the bond. Look at this, how to calculate. So if they ask what is the kinetic energy of A atom. So kinetic energy of A atom is not the 10 kilojoules. Why? Because 40 kilojoules we are giving, 30 kilojoules were used by the molecule to separate the atoms. And now both of atoms are absorbing the remaining 10 kilojoules. Imagine 5 kilojoules each absorbed. So now the kinetic energy of the every atom is equals to 5 kilojoules, not the 10 kilojoules. So how to calculate means here you can see that kinetic energy is equals to energy of the incident light is equals to 40 kilojoules minus bond energy we have taken as 30 kilojoules divided by number of atoms involved in this bond. Usually 2 will be there. So 2 that equals to 10 by 2 equals to 5 kilojoules per atom is the kinetic energy. So I hope you understand this photoelectric effect. Let us continue one more part, that is application of this photoelectric effect. So I'll erase this diagram. So sometimes there are some questions which looks similar to the photoelectric effect, but they are not photoelectric effect concepts. So let us imagine that they had given one atom where some electrons are present. So this atom was hit by some light of wavelength lambda I, and afterwards electron undergo both excitation and de-excitation. Means electrons are not coming out of the atom. So electron absorbed that energy and it went to the higher energy level, and while coming back it is releasing the two wavelengths, two type of the photons. So two photons are released by the electron while it coming to the lower energy level. So that it is releasing the two wavelengths lambda 1 and lambda 2. Imagine lambda I value was given, lambda 1 value is given, but lambda 2 value not given. That has to be calculated. In such conditions, directly we should not take the wavelengths. Wavelengths are not summed. We can sum the only energy. So that let us consider this one as the energy of the incident light. This is the energy of the first photon, energy of the second photon. So that energy can be added. So energy of the incident light is equals to E1 plus E2, total energy. So EI means that is H nu I is equals to H nu 1 plus H nu 2. Nu means again C by lambda. So that directly we can write down that HC by lambda I is equals to HC by lambda 1 plus HC by lambda 2. HC cancel out. We need to calculate the lambda 2. So that's why 1 upon lambda 2 is equals to 1 upon lambda I minus 1 upon lambda 1. So 1 upon lambda 2 is equals to lambda 1 minus lambda I divided by lambda 1 lambda I. But our intention is not to calculate 1 upon lambda 2. We have to calculate the lambda 2. So that lambda 2 value is equals to, just reverse this one. We get the lambda 1 lambda I divided by lambda 1 minus lambda I. So using this type of relations, we can solve the questions that is related to the, it is similar to the photoelectric effect, though it is not the photoelectric effect. Why? Because no electrons are emitted or ejected. I hope you understand this today's class. So we shall meet in the next class. Thank you.